Hey everyone, and welcome back to The Explainer. Today, we're diving into something that is literally a paradigm shift in 3D CT scan analysis. We are talking about moving away from this broad, global AI understanding to razor-sharp anatomical precision. It's a brand new method called ConQuer, and it powers an incredibly impressive new foundation model called Jolia. You're going to want to stick around for this one. Here is our quick roadmap for today. We'll start with the medical AI problem, introduce concept queries, break down exactly how ConQuer works, evaluate Jolia's performance, look at radiology report generation, and finally, peek into the future of Jolia. Section 1. The medical AI problem. Compressing complexity. Let's jump right in. To really understand why this research matters, we kind of have to look at how medical AI currently struggles to process massive amounts of biological data. Foundation models have obviously transformed machine learning, but medical imaging? It presents a very unique, insanely dense challenge. Right now, the dominant recipe is something called standard clip-style pre-training. Basically, it's a vision-language approach that encodes an entire image and its corresponding text report into a single global vector token. To put that into perspective, imagine reading a dense 1,000-page medical textbook and being forced to summarize the whole thing in a single word. That is exactly what standard clip-style models do to these massive 3D CT scans. When you compare these two realities, the problem becomes super obvious. A global CT scan spans dozens of distinct organs. It comes with multi-sectioned reports detailing hyper-localized findings, like a 2-centimeter cyst specifically in the liver. But standard models compress all of these structural axes into one single data point. Compressing that vast amount of structured data into a single token practically guarantees that crucial, localized details are just going to get totally lost in translation. And this brings us to a massive roadblock. If compressing data destroys the detail, but trying to use human-drawn spatial segmentation masks is way too expensive and limiting, how do we build a system that inherently understands local anatomy? Essentially, how do we teach AI to see the anatomical trees and not just the global forest? Section 2. Introducing concept queries, the localized fix. So this brings us to the elegant solution proposed by the researchers. They call it concept queries, or ConQuer for short, which is a fantastic name, by the way. This is the localized fix to that global compression problem we just talked about. ConQuer bridges the gap by decomposing both the image and the text report into a parallel set of concept-level alignments. Instead of one massive summary, it specifically targets anatomical regions, like the liver or the lungs. It forces the model to learn parallel contrastive alignments for every single concept independently. Section 3. How ConQuer works. Breaking down the pipeline. Let's move under the hood to see exactly how this architecture is put together. And remember, the real magic here, the whole shebang, is that it achieves this without relying on expensive, human-annotated segmentation masks. The pipeline operates in 3 really precise steps. Step 1 is LLM data processing, where they use a language model to split the long clinical report into concept-specific sections. Step 2 is cross-attention pooling. Here, learnable queries pool matching visual features directly from the image encoder for each specific organ. And finally, step 3 is contrastive alignment. The model aligns those text concepts and visual features independently, so it learns what a healthy liver looks like versus a liver with cirrhosis, completely independently from how it looks at the lungs or the kidneys. What is honestly mind-blowing about this is the sheer efficiency of the method. Zero spatial supervision is required. Absolutely none. These cross-attention queries learn to find the organs entirely on their own, requiring zero human-drawn spatial bounding boxes. And if you look at the computational cost, adding these concept queries only adds about 0.6 million parameters. That is literally just a 1 to 3% overhead on the model size, but it gives you a massive, massive gain in structural understanding. Section 4. Evaluating Jolia's performance. Benchmarking the impact. Okay, so let's look at what happens when the ConQuer method is actually used to train a brand new 3D CT foundation model. The researchers named this new model Jolia, and they put it to the test on both chest and abdominal CT datasets. For the evaluation, Jolia uses what's called a finding-anchored representation. It cleverly combines the global understanding of the scan, the big picture, with the hyperspecific feature data of the targeted organ, meaning if the model is looking for cirrhosis, it anchors specifically to the liver features. It's not just blindly scanning the whole image, it knows exactly where it should be looking. When we look at the linear probing results for finding classification, which basically tests how good the frozen, pre-trained model is at identifying specific abnormalities, Jolia consistently sets a completely new state-of-the-art. On the Merlin abdominal dataset, it scores an 83.59, and on the CT rate chest dataset, it hits an 86.44. It is outperforming major established baselines like CT Clip, Spectre, and Pillar 0 across the board. But I want to draw your attention to this massive leap right here. Jolia beat the segmentation-based FVLEM model by an impressive 9.4 points on external chest scan evaluations. Why is that a big deal? Well, because FVLEM relies on explicit, heavily supervised anatomical decomposition via segmentation masks. Jolia doesn't. Jolia beat a heavily supervised model using a mask-free, zero-spatial supervision approach. That is an absolute game-changer for scaling up medical AI without breaking the bank on annotations. You can see how intuitive it is when you look at this mapping protocol. Jolia isolates the pathology by directly anchoring the concept of a finding to an organ. So cirrhosis goes solely to the liver features. Tracheal narrowing is anchored solely to the lungs. It is quite literally teaching the AI to think and look at scans exactly like a human anatomist would. Section 5. Generating radiology reports. Clinical fidelity. Identifying findings is one thing, right? But translating those visual AI capabilities into actionable, written text for real clinicians, that is the ultimate test for a foundation model. The researchers paired Jolia with a language model to generate written findings from the CT volume alone, and Jolia absolutely dominated the standard natural language benchmarks. It secured the highest Blue, Rougeol, and BERT scores. But perhaps the most crucial stat here is that it achieved the best green score. Green is a metric specifically designed to evaluate clinical fidelity. So Jolia proves it doesn't just see the abnormalities better, it actually describes them more accurately. And honestly, most impressively, Jolia achieved a 34% relative gain on the RADgraph F1 metric over the previous leading model, Merlin. Standard text metrics can sometimes miss the mark in medicine. I mean, missing a single tiny word like no can change a diagnosis entirely. But RADgraph F1 actually measures clinical entity overlap, meaning Jolia has a vastly superior grasp of identifying and accurately stating the correct medical entities in its reports. A 34% jump is just huge. Section 6. The future of Jolia, scaling concept alignment. Having established Jolia's dominance in identifying findings and generating reports, we really have to consider where this architecture goes next, because the implications are vast. The research paper leaves us with this really profound insight. The load-bearing ingredient is localization itself, not the specific concepts. See, the researchers actually ran tests using just arbitrary clusters instead of specific organs, and the performance still improved over the baseline. The secret sauce is the very act of forcing the AI to localize its attention. This means the ConQuer methodology is incredibly adaptable to other medical fields. Think MRI or mapping tumor subtypes, all because it inherently forces the AI to look at the component parts, not just the massive whole. As we wrap up this explainer, the data leaves us with a genuinely thrilling thought. We've just watched an AI model learn to perfectly navigate the highly complex structures of the chest and abdomen without a single human drawing a spatial map for it. If we can achieve this unprecedented level of diagnostic precision purely through text-to-image concept alignment, how quickly can we map the entire human anatomy? The foundation has definitely been laid, and the next leap in medical AI is clearly localized. Thanks so much for joining me on this deep dive, and I'll see you in the next one.